When we launch the application, we can load an existing model. For that, we can go on Input, Output, Load, navigate to our folder, and choose our gene regulatory network. This will automatically load the node model that has been used to generate that circuit. So in this case, Tomatsu. Since visual representation is important when working with gene regulatory networks, especially as they become increasingly complex, GRN modeler allows us to adjust these settings. For that, we can go on Settings, Graph Settings, and here we can play around with sizes and colors of the various elements. So for example, I could make my nodes bigger and green and adjust the font size. Then save and close. Also, the layout of the representation by default is force, but there can be other type that might be relevant for different kind of circuits. To navigate that, we can right-click on the graph. A drop-down menu appears where we can select different kinds of layout. At any moment, it's possible to go back to the original settings by clicking on Load Default. Also, the GRN Modeler app allows to see a different kind of representation of the interaction, which we can explore by clicking on Use the Original Graph button. In this case, instead of having arrows for activation, T-shape lines for repression, and lines for protein degradation, we just have arrows of different colors. Green for activation, red for repression, and dotted gray for protein degradation. For today, we will stay with the original settings though. So feel free to explore the different graphical layouts that are available. The other very important thing that we can modify are the settings of each element, so the parameters of the circuit. For that, we can click on any element that will appear in the appropriate box, and we can now click on Set. That will open a new tab. Once we're here, we can easily navigate through all the components, node, protease, and regulator that appear as drop-down menu. We also have the Cell tab, which allows us to change the cell volume, which we can make bigger, for example. Keep in mind that in the current version of the app, we are modeling circuits based on molecule numbers and not concentration, so changing the volume of the cell will not impact the simulation. If we try to change tab without saving the parameters changes, a window pops up to ask if we're sure. In this case, I will simply discard these changes and move on. Let's have a look at the Node tab. Don't let yourself be overwhelmed by all this information. We can actually modify only few of these things, but these are all important pieces of information about the node. What we can modify is just the initial amount column and the value column. So let's have a look at the initial amount. We have initial amount for the mRNA, for the unfolded protein, and for the folded protein. As for the value, these are parameters that describe the node, that are described by a name. If we are uncertain what these parameter name refer to, we can have a look at the reaction section and see where these parameters appear. So for example, this K-mat appears in the third reaction that describes the maturation from unfolded protein to folded protein. So making this value bigger will make the maturation faster and vice versa. Every time you change a value, make sure you save the current changes. These three columns tells us important pieces of information about the variable we are looking at. Units tells us the nature of the variable, whether it is a molecule, a rate constant, or something else. The constant box tells us whether that variable will change throughout the simulation or if it needs to stay constant. The level of unfolded and folded protein, for example, are unchecked here because they will change throughout the simulation. Vice versa, some elements will remain constant. For example, the degradation rate of mRNA molecules will not change during the simulation. Finally, the last column tells us whether parameter is individual, meaning it is specific for the node, for the element we are working on, or if it's common, meaning that changing this parameter would affect other elements as well. So for example, changing the protein product of node 1 will not affect any other nodes, while setting the mRNA degradation to a new value and saving will actually modify the same value in all other tabs. Okay, let's have a quick look also at the protease and the regulator tab. As for the regulator, we can see the protein product of that regulator and 4 parameters. As for the protease, we can see the initial amount of the protease itself and of all the elements that are subject to degradation, so unfolded and folded protein for each of the nodes. Each reaction here describes degradation of these elements using 5 parameters in total. An important note is that these constant box and these common or individual is described at the node model level. So if you need to change some of these, for example, you need to make a parameter common or vice versa, you need to override the node model. Okay, once we're happy with the parameter that we have set, we can save and close. And then make sure that you save your final circuit. You can either override your existing model or create a new one in case you're interested in comparing the simulation with different sets of parameters. So with this, we're happy. In the next video, we will see how to run deterministic and stochastic simulation on the circuits that we have created.